The universe is hiding something big, something we can't even see. Picture this: what holds galaxies together, what shapes the very fabric of space, isn't the stars or the planets. It's something invisible, something mysterious. Dark matter, it's out there, weaving an enormous cosmic web that holds everything in place, yet we still don't know what it truly is, and that's just the beginning. Today, we're diving into 25 of the biggest mysteries about this cosmic shadow: why it's missing where it should be, how it bends light without being seen, and whether it could rewrite the laws of physics as we know them. Think of the universe like a grand puppet show, and dark matter is the unseen hand pulling the strings. Without it, galaxies would fly apart, stars would drift into the void, and the universe as we know it wouldn't exist. Yet, despite its massive role, it refuses to show itself. That's what makes this so fascinating. We're chasing a ghost that makes up most of the universe. So buckle up, because by the end of this journey, you'll see space in a whole new way. We'll uncover strange galaxies with no stars, debate whether dark matter could be from another dimension, and even explore if it's whispering secrets through gravitational waves. Ready to unravel the invisible? Let's go. Now let's tackle the first and perhaps most baffling mystery of them all: the missing mass problem. Imagine looking at a spinning carousel. The faster it spins, the harder it is to keep the riders from flying off. Galaxies work the same way. Stars on the outer edges should be flung into space if gravity were only coming from the visible matter we see, like stars and gas. But they aren't. Something invisible is holding them in place. That something is dark matter. This puzzle didn't just pop up overnight. Back in the 1930s, a sharp-eyed astronomer named Fritz Zwicky noticed something strange about galaxy clusters. He calculated how much gravity should be holding them together based on the visible stars and gas, but the numbers didn't add up. The galaxies were moving way too fast, so fast that they should have torn apart long ago. Zwicky called this missing mass Dunkle Materie, or dark matter, and though his ideas were largely ignored at the time, he was onto something huge. Fast forward to the 1970s, and another breakthrough came from Vera Rubin. She studied the rotation of spiral galaxies and found the same weird pattern. Stars at the edges weren't slowing down like they should. Instead, they were zipping around just as fast as stars near the center. The only explanation: an invisible halo of dark matter wrapping around galaxies like a hidden hand, keeping everything in place. But how do we know dark matter is real if we can't see it? Here's where things get even more fascinating. One of the strongest pieces of evidence comes from something called gravitational lensing. When light from distant galaxies passes through a massive galaxy cluster, the cluster's gravity bends the light, distorting the images behind it, almost like a cosmic magnifying glass. But here's the kicker: the distortion is way stronger than what the visible matter alone could cause. That extra bending, it's the fingerprint of dark matter. Then there's the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter clumped together in the early universe. And guess what? The pattern matches a universe where dark matter makes up about 27% of everything, while ordinary matter, the stuff we see, accounts for less than 5%. The rest, that's dark energy, but that's a story for another day. So why haven't we caught dark matter yet? That's the million-dollar question. It doesn't emit, absorb, or reflect light, and it barely interacts with normal matter except through gravity. It's like trying to catch smoke with your bare hands, but scientists aren't giving up. Experiments deep underground, like Xenon and Lux, are hunting for rare collisions between dark matter particles and ordinary atoms. Meanwhile, particle colliders are smashing atoms together at insane speeds, hoping to create dark matter in the lab. The missing mass problem isn't just a scientific curiosity, it's a cosmic wake-up call. Everything we see, from the tiniest star to the largest galaxy, is just the tip of the iceberg. The real universe, the one shaping existence itself, is hiding in plain sight. And as we peel back the layers, we're not just solving a mystery, we're rewriting the story of everything. Now let's turn our attention to the invisible fingerprints dark matter leaves behind. Think of it like this: you can't see the wind, but you know it's there when leaves rustle or branches sway. Dark matter works the same way. It doesn't glow or cast shadows, but its gravitational tug betrays its presence in some truly spectacular cosmic phenomena. Take galaxy rotation curves, for instance. We touched on Vera Rubin's groundbreaking work earlier, but let's dig deeper. Picture a merry-go-round again. If it were made only of visible matter, stars and gas, the outer edges would spin slower than the center, just like planets farther from the sun move more sluggishly. But Rubin's observations shattered that expectation. Stars at the edge of spiral galaxies whip around just as fast as those near the core, defying the laws of gravity as we knew them. The only way this makes sense: a massive, invisible halo of dark matter enveloping the galaxy, providing the extra gravitational muscle to keep those outer stars in check. Then there's gravitational lensing, one of the most dramatic ways dark matter gives itself away. Imagine looking through a glass of water and seeing a straw appear bent. On a cosmic scale, galaxy clusters act like that warped glass. Their immense gravity bends light from distant galaxies behind them, distorting their shapes into smears and arcs. But here's the mind-bending part. When astronomers map these distortions, they often find that most of the lensing effect comes from places where there's no visible matter. That's dark matter's signature, a ghostly scaffold bending spacetime where nothing seems to exist. The Bullet Cluster is perhaps the most famous smoking gun. This pair of colliding galaxy clusters is a cosmic crime scene where dark matter's fingerprints are crystal clear. When the clusters smash together, their hot gas, the visible matter, piled up in the middle, slowed by friction. But the bulk of their mass, revealed by gravitational lensing, kept right on going, sailing past the gas like two ghosts passing through each other. This eerie separation proved dark matter isn't just a mathematical fix, it's a real, physical thing that interacts differently from normal matter. But dark matter's clues aren't limited to the here and now. The cosmic microwave background, that faint glow from the infancy of the universe, holds secrets too. Tiny ripples in this afterglow reveal how matter clumped together in the early cosmos. Without dark matter's gravitational pull, those ripples wouldn't have grown into the vast cosmic web we see today. The pattern matches a universe where dark matter outweighs ordinary matter by more than 5-to-1, a ratio etched into the sky just 380,000 years after the Big Bang. So what does all this tell us? Dark matter isn't just a placeholder for our ignorance. It's a dynamic, invisible architecture shaping everything from individual galaxies to the large-scale structure of the universe. And while it refuses to play by the rules we're used to, its gravitational whispers are loud enough to guide us closer to the truth. The hunt continues, but one thing's certain: the cosmos is far stranger and far more clever than we ever imagined. Now let's venture into the heart of the hunt, the quest to pin down dark matter's true identity. If it's out there shaping galaxies and bending light, what is it made of? Scientists have turned detective, chasing down leads on particles that could solve this cosmic whodunit. The prime suspect for decades has been WIMP, weakly interacting massive particles. These hypothetical heavyweights would be shy, barely interacting with normal matter except through gravity and maybe the weak nuclear force. Picture a room full of people where most are chatting, but WIMP would be the silent figures slipping through unnoticed. Their mass could explain dark matter's gravitational grip, while their reluctance to interact would account for why we can't see or feel them. To catch these elusive particles, experiments like Xenon 1T and LUX went deep, literally. Shielded by layers of rock and water to block cosmic noise, their detectors filled with ultra-pure liquid xenon wait for the faintest flicker, a WIMP bumping into a xenon atom. Imagine listening for a single raindrop in a thunderstorm. That's the level of precision needed. Yet despite years of searching, these underground labs have turned up empty-handed. The latest upgrades, like Xeno NNT, are pushing sensitivities further, but WIMP remain ghosts in the data. Enter the underdog candidate, actions. These featherweight particles were dreamed up to solve a puzzle in quantum physics, but they fit snugly into the dark matter mystery. Unlike WIMP, actions would be billions of times lighter, possibly forming a faint, galaxy-spanning wave. To find them, experiments like ADMS use powerful magnetic fields to coax actions into revealing themselves as tiny bursts of microwave light. It's like tuning a radio to catch a whisper from the cosmos. While no confirmed signals have appeared yet, actions offer a compelling alternative if WIMP keep dodging detection. Why is this search so tough? Dark matter's reluctance to interact is both its defining trait and our biggest hurdle. Even if trillions of these particles stream through you every second, they'd pass like starlight through glass. Experiments must drown out background noise from cosmic rays, radioactive decay, even the faint warmth of their own equipment. It's a needle in a haystack challenge where the haystack keeps growing. Yet the stakes couldn't be higher. Discovering dark matter's particle would rewrite physics, revealing a hidden layer of reality. Some theories even suggest we're chasing multiple culprits, a mix of WIMP, actions, or something entirely unexpected. As detectors grow more sensitive and ideas more creative, one thing's clear. The universe loves a good mystery, but it never plays unfair. The clues are out there waiting for the right moment and the right experiment to crack the case. Next, we'll unravel how this invisible scaffolding weaves the cosmos into the vast cosmic web we see today. But for now, the hunt continues, with every null result narrowing the path to a breakthrough. Now, let's step back and see the bigger picture the grand architecture dark matter builds across the cosmos. Imagine the universe as a bustling city with galaxies as neighborhoods. But what holds these neighborhoods together? The answer lies in an invisible framework, a cosmic skeleton woven by dark matter. Scientists call this the cosmic web, and it's the largest structure in existence. Picture a spider's silk stretched across billions of light years, with galaxies clinging to its strands like dewdrops. These strands, or filaments, are the highways of the universe, where dark matter's gravity pulls gas and stars into dense ribbons. Between them, vast, empty voids, some so large they could swallow thousands of Milky Ways. This eerie balance of crowded filaments and gaping voids is dark matter's masterpiece. But how do we map something we can't see? Supercomputer simulations like the Millennium Run or Illustris TNG act as time machines, tracing how dark matter's gravity sculpted the universe from the Big Bang to today. Feed in the known laws of physics, and these simulations predict a web eerily similar to what telescopes observe. In them, dark matter starts as a faint ripple in the early universe. Over eons, gravity amplifies those ripples, clumping matter into halos where galaxies later form. The halos connect like beads on a string, forming filaments, while the emptier regions stretch into voids. One real-world clue to this hidden scaffolding comes from galaxy surveys like the Sloan Digital Sky Survey. By mapping millions of galaxies, astronomers see the same web-like patterns the simulations predict. But here's the twist: galaxies are just the tip of the iceberg. They trace the densest knots in the web, while dark matter's filaments, far more extensive, remain invisible. To detect those, scientists use gravitational lensing, where the filament's mass bends light from distant objects, warping their images like a funhouse mirror. The cosmic web isn't static either. Filaments funnel gas into galaxies, fueling star birth, while voids grow emptier as matter drains away. Some voids even have a mysterious, repulsive effect, pushing galaxies outward, a phenomenon still poorly understood. And the web's structure holds clues to dark matter itself. Cold dark matter, for example, predicts more small-scale filaments than warm dark matter, which would smear out fine details. What's next? Projects like ESA's Euclid telescope aim to chart the web in 3D, measuring how dark matter's distribution has evolved over cosmic time. Combine that with sharper simulations, and we might finally decode how this invisible skeleton assembled the universe as we know it. Up next, we'll confront a radical idea: what if dark matter isn't the answer at all? Some scientists argue we've been misreading the cosmos's clues, and the truth lies in rewriting gravity itself. But for now, one thing's certain: without dark matter's cosmic web, the universe would be a very different and far lonelier place. But what if we've been reading the cosmos all wrong? Let's tackle a bold idea that challenges the very foundation of dark matter. What if gravity itself operates differently than we think? Some scientists argue that the mysteries we blame on invisible matter might actually be flaws in our understanding of gravity. Enter modified Newtonian dynamics, or MUND, a theory that rewrites the rules to explain the universe without dark matter. MUND's starting point is simple. When we observe galaxies, their outer stars rotate at speeds that defy Newton's laws. According to classic physics, these stars should slow down as they get farther from the galaxy's center, like planets in our solar system. But instead, they whip around just as fast as inner stars, as if gripped by some unseen force. Dark matter explains this by adding invisible mass, but MUND proposes a radical fix: adjust gravity's math at extremely low accelerations, the kind found in galaxy outskirts. Tweak the equation, and suddenly the star's speed makes sense without invoking hidden matter. And MUND has had its wins. For certain galaxies, especially dwarf and low-density ones, its predictions match observations startlingly well, sometimes better than dark matter models. Take the famous Tully-Fisher relation, which links a galaxy's brightness to its rotation speed. MUND nails this correlation naturally, while dark matter requires fine-tuning of halo shapes to fit. Then there's the bulletproof galaxy NGC 1052-DF2, which spins so slowly it seemingly lacks dark matter altogether. For MUND supporters, this isn't a puzzle, it's proof their theory works. But here's the catch: while MUND excels at galaxy-scale puzzles, it stumbles on bigger cosmic stages. Take galaxy clusters, where visible matter accounts for just a fraction of the gravity needed to hold them together. MUND adjustments can't fully bridge that gap, forcing its proponents to grudgingly admit some extra mass might still be required, a shadow of the very dark matter they aim to replace. Then there's the cosmic microwave background, the afterglow of the Big Bang. Its intricate patterns align perfectly with dark matter-based models, but leave MUND scrambling to keep up. The biggest blow: gravitational lensing. When massive objects bend light, the amount of bending depends on total mass. In cases like the Bullet Cluster, where colliding galaxies separate visible gas from their gravity sources, MUND can't explain the lensing unless it smuggles in unseen mass, effectively reinventing dark matter under another name. So where does this leave us? MUND remains a fascinating underdog, a reminder that science thrives on questioning even our most cherished ideas. It pushes dark matter theorists to sharpen their models, ensuring they're not just patching gaps with invisible putty. But for now, the cosmic scales tip toward dark matter's side. It's the only framework that explains everything from galaxy rotations to the universe's largest structures without constant ad hoc fixes. Still, the debate isn't over. Upgraded telescopes and simulations keep testing both sides, and who knows, maybe future data will reveal a third option we haven't even imagined yet. But one thing's certain: whether through unseen matter or rewritten physics, the universe still guards its deepest secrets closely. Now, let's turn to a cosmic paradox that flips expectations on their head. Galaxies so massive they shouldn't exist, yet here they are, defying every rule in the book. Now, let's shift our gaze to one of the universe's most baffling anomalies: galaxies that shouldn't exist. Picture a galaxy so faint, so ghostly, that it barely registers against the cosmic backdrop, yet somehow it holds the gravitational might of a cosmic giant. This is the enigma of ultra-diffuse galaxies, and Dragonfly 44 is their poster child. Discovered in 2015, Dragonfly 44 is a cosmic contradiction. Spanning as wide as the Milky Way, it contains less than 1% of our galaxy's stars, making it nearly invisible. If you replace the Milky Way with Dragonfly 44, the night sky would be almost empty, with stars spaced so far apart you'd need a telescope to spot your nearest stellar neighbor. Yet, despite this ghostly appearance, something massive lurks within it. When astronomers measured the motions of its few stars, they found them whipping around at speeds that shouldn't be possible without an immense gravitational anchor. The culprit, a dark matter halo weighing a staggering 1 trillion times the mass of our Sun, nearly as much as the Milky Way's, but with almost none of the stars. This discovery sent shockwaves through astrophysics. How could a galaxy so faint harbor so much unseen mass? Traditional models struggle to explain it. Dark matter theories suggest halos should attract gas, forming stars, yet Dragonfly 44's halo remains eerily empty. Some propose it's a failed galaxy, where dark matter clumped together but star formation fizzled out. Others wonder if extreme tidal forces from neighboring galaxies stripped away its stars, leaving only the dark skeleton behind. But here's the twist: Dragonfly 44 isn't alone. Dozens of similar ultra-diffuse galaxies have been found, each with the same bizarre imbalance of invisible mass and visible scarcity. The implications are profound. If dark matter can pool so densely without forming stars, it challenges our understanding of how galaxies evolve. It also raises a tantalizing question: could there be even darker galaxies out there, completely starless and invisible, detectable only by their gravitational whispers? In fact, some researchers speculate that Crater 2, a mysterious dark galaxy near the Milky Way, might be just that, a pure dark matter entity. Yet Dragonfly 44 isn't just a cosmic oddity, it's a litmus test for competing theories. Modified Newtonian dynamics, or MUND, struggles here. Without dark matter, man can't easily explain how such a sparse galaxy generates enough gravity to keep its stars racing. Meanwhile, dark matter models face their own hurdles, like why these halos didn't birth more stars. The hunt for answers continues. New telescopes like the Vera Rubin Observatory are scanning the skies for more of these shadowy giants, while simulations refine how dark matter behaves in extreme environments. Each discovery peels back another layer of the mystery, revealing how much we still don't understand about the invisible threads weaving the cosmic web. As we ponder these ghostly giants, let's venture into another puzzle, where dark matter might not just shape galaxies but power them in ways we never imagined. Now let's untangle another cosmic puzzle, one that hinges on speed. Picture dark matter not as a single, uniform entity, but as particles with different temperatures, each racing through the universe at its own pace. This is the great divide between cold and warm dark matter, and it holds the key to understanding why galaxies form the way they do. Cold dark matter is the slow-moving heavyweight of the cosmos. Imagine particles lumbering through space at speeds far below light's blistering pace. Because they're sluggish, they clump together easily under gravity's pull, forming dense halos that act as gravitational anchors for galaxies. This theory has been the gold standard for decades, neatly explaining the universe's large-scale structure, like the vast filaments of the cosmic web and the way galaxies cluster together. Supercomputer simulations based on cold dark matter, such as the famous Millennium Run, recreate these structures with stunning accuracy, but there's a catch. When zooming in on smaller scales, cold dark matter hits snags. It predicts an overabundance of dwarf galaxies orbiting large ones like the Milky Way, far more than we've observed. It also struggles to explain why some ultra-diffuse galaxies like Dragonfly 44 have such extreme dark matter densities without corresponding starlight. These wrinkles in the theory have led scientists to explore an alternative warm dark matter. Here, particles zip through space faster, closer to the speed of light. This extra energy prevents them from clumping as tightly, smoothing out small-scale structures. Warm dark matter would suppress the formation of tiny dwarf galaxies, potentially solving the missing satellites problem. It might also explain why some galaxies seem to have dark matter halos that are more spread out or fluffy compared to cold dark matter's predictions. The leading candidate for warm dark matter, sterile neutrinos, hypothetical particles that don't interact with ordinary matter at all except through gravity. Unlike their ordinary neutrino cousins, which flit through your body by the trillions every second, sterile neutrinos would be far heavier and slower, but still too speedy to qualify as cold dark matter. Experiments like the upcoming James Webb Space Telescope are hunting for indirect clues, such as odd patterns in the light from distant quasars that might betray sterile neutrinos' presence. Yet warm dark matter isn't a perfect fix either. While it eases some small-scale tensions, it can't fully replicate the cosmic web's intricate filamentary structure seen in cold dark matter simulations. Some researchers propose a middle path, a mix of both types, or even fuzzy dark matter, where particles behave like quantum waves on cosmic scales. The stakes are high. If dark matter is cold, galaxy formation is a top-down process, with massive structures collapsing first and fragmenting into galaxies. If it's warm, small structures form later, potentially altering the timeline of cosmic evolution. The answer could reshape our understanding of everything from the first stars to the fate of galaxy clusters. As we weigh these invisible contenders, another mystery tugs at the edges of our knowledge, one hidden in the heart of our own galaxy. The Milky Way's dark halo holds secrets of its own, from lopsided distributions to ghostly subhalos lurking just beyond the light. Now, let's turn our gaze closer to home, where the Milky Way's own dark matter halo holds secrets that challenge even our best cosmic theories. This invisible shroud enveloping our galaxy isn't just a smooth, featureless cloud. It's a dynamic, uneven structure with quirks that keep astronomers up at night. Take its lopsided distribution for starters. If dark matter were perfectly symmetrical, we'd expect it to be evenly spread around the Milky Way like a spherical shell. But observations tell a different story. The halo is lumpy, with denser patches in some regions and surprising gaps in others. One leading explanation: ancient collisions. Our galaxy has a violent history of swallowing smaller ones, and each merger leaves behind debris clumps of dark matter that haven't fully mixed into the halo. It's like stirring cream into coffee but finding stubborn swirls that refuse to blend. Then there's the enigma of Crater 2, a so-called dark galaxy lurking just beyond the Milky Way's visible disk. Discovered in 2016, this faint dwarf galaxy is so diffuse that it's nearly invisible, yet it weighs more than some globular clusters. How its dark matter content is staggering. Crater 2 stars move far too slowly for their apparent mass, implying a hidden gravitational anchor, a dense knot of dark matter. But here's the twist. According to cold dark matter models, subhalos like Crater 2 should be far more common than we've observed. Its existence fits the theory, but its rarity doesn't. This discrepancy ties into the larger missing satellites problem we touched on earlier. Simulations predict thousands of tiny dark matter clumps orbiting the Milky Way, yet we've spotted only a few dozen dwarf galaxies. Some suggest these missing subhalos might simply be too dark to see, lacking enough stars to light them up. Others argue that early cosmic radiation blasted away their gas, preventing star formation altogether. Either way, Crater 2 stands as a tantalizing clue, proof that dark matter structures can exist in near total darkness. But the Milky Way's halo isn't just about what's there. it's also about what isn't. Recent studies of hypervelocity stars ejected from the galaxy's center at breakneck speeds reveal something odd. Their trajectories suggest the inner halo might be less dense than expected, almost as if dark matter is avoiding the galactic core. Could supermassive black holes be scouring it away, or is dark matter interacting with itself in ways we don't yet understand? The answers might lie in upcoming projects like the Vera Rubin Observatory, which will map millions of stars to trace the halo's gravitational imprint with unprecedented precision. Meanwhile, experiments like LZ and Panda X continue hunting for dark matter particles right here on Earth, hoping to catch a whisper of the halo's hidden substance. As we peel back these layers, another puzzle emerges, one that flickers at the edge of detection. Strange gamma-ray signals from the galactic center have sparked debates. Could they be the long-sought glow of dark matter particles annihilating one another? That's where we're headed next, into the heart of a cosmic detective story that's anything but black and white. Now, let's venture into one of the most electrifying chapters of the dark matter saga, the hunt for annihilation signals. Picture this: deep in the heart of our galaxy, an unexplained glow of gamma rays pulses with a rhythm that defies ordinary astrophysics. Could this be the smoking gun of dark matter particles crashing into one another, unleashing energy as they vanish? The story begins with the Fermi Gamma Ray Space Telescope, which has spent over a decade scanning the sky for these high-energy photons. What it found in the galactic center was startling: an excess of gamma rays that couldn't be fully explained by known sources like pulsars or cosmic rays slamming into gas. The energy of these photons, clustering around a specific range, eerily matches predictions for certain types of dark matter particles, particularly those called weakly interacting massive particles, or WIMP. According to theory, when two WIMP collide, they could annihilate each other, transforming into gamma rays in a flash of light. But here's where things get messy. The galactic center is a crowded, chaotic place packed with alternative gamma ray factories. Young, spinning pulsars, city-sized corpses of dead stars, spew out similar radiation. Turbulent gas clouds lit up by cosmic rays can mimic the signal. Even a population of faint, unresolved millisecond pulsars could collectively produce the excess. So, is this dark matter's calling card, or just cosmic background noise? Scientists have turned to clever tricks to test the dark matter hypothesis. One approach looks at the gamma rays' spatial distribution. If they are from dark matter annihilations, they should follow the expected shape of the Milky Way's dark matter halo, smoother and more spread out than the clumpy emission you'd get from point sources like pulsars. Early analyzers seemed to support this, but later studies argued the signal's patchiness better fits pulsars. Then there's the energy spectrum, the fingerprint of the particles involved. Some models of dark matter predict a sharp drop-off at certain energies, which Fermi's data tantalizingly hints at, but again, it's not conclusive. The plot thickens when we zoom out to other galaxies. Dwarf spheroidal galaxies orbiting the Milky Way, like Draco or Ursa Minor, are perfect test beds. They're teeming with dark matter, but have almost none of the messy astrophysical sources that plague the galactic center. If dark matter annihilates, these dwarfs should glow faintly in gamma rays. Fermi has checked intensely, and so far, silence, not the faintest whisper of a signal. This absence doesn't rule out dark matter annihilations in the Milky Way's core, but it does raise eyebrows. If the galactic center excess is real dark matter, why don't the dwarfs show it too? Enter the contrarians. Some theorists propose that the signal isn't from WIMP at all, but from a different dark matter candidate actions. These ultralight particles could convert into gamma rays in the presence of strong magnetic fields, like those near the supermassive black hole Sagittarius, a star. Others suggest more exotic possibilities, like dark electromagnetism, where dark matter particles interact via unknown forces, leaving unique imprints in the gamma ray sky. The debate reached a fever pitch in 2020 when a team using NASA Fermi data claimed to spot gamma-ray lines, sharp spikes at specific energies that could only come from dark matter annihilation. The excitement was short-lived. Independent analyzers couldn't reproduce the result, attributing the lines to statistical fluctuations or instrumental effects. Yet the allure remains. Future telescopes like the upcoming Cherenkov Telescope Array could settle the argument with unprecedented sensitivity, peeling apart the gamma-ray fog to isolate dark matter's true signature. What makes this search so thrilling is the stakes. Catching dark matter in the act of annihilation wouldn't just confirm its existence, it would reveal its identity. The energy of the gamma rays would tell us the particle's mass. The signal's shape would expose how it clusters in space. It's like hearing a shadow speak, and in its voice unlocking the blueprint of the invisible universe. But for now, the galactic center's gamma-ray excess remains a riddle wrapped in a mystery. Is it the faint echo of dark matter's demise, or just the cosmic hum of mundane astrophysics? The answer, like dark matter itself, still hides in plain sight. Now, let's shift our gaze to one of cosmology's most puzzling dilemmas, the Hubble tension, and how dark matter might be pulling the strings behind the scenes. Imagine measuring the speed of a car with two different methods, only to get wildly different results. That's essentially what's happening with the universe's expansion rate, and dark matter could be the unexpected wrench in the works. The story starts with the Hubble constant, the number that tells us how fast the universe is expanding. For decades, scientists have calculated it in two primary ways. The first method looks at nearby galaxies and supernova, using their brightness and distance to gauge expansion. The second method studies the afterglow of the Big Bang, the cosmic microwave background, and extrapolates forward using our best models of the universe's evolution. Here's the catch: these two approaches disagree. The cosmic microwave background suggests a slower expansion, while local measurements insist it's faster. This discrepancy is the Hubble tension, and it's got scientists scratching their heads. Enter dark matter. If the universe's expansion isn't behaving as predicted, perhaps dark matter isn't playing by the rules we've assumed. One intriguing idea is that dark matter might interact with itself or other cosmic components in ways we haven't accounted for. For example, if dark matter particles occasionally collide or exchange energy, this could subtly alter how structures form and how the universe expands over time. Some theories even propose that dark matter's properties could change as the universe ages, throwing a curveball into our measurements. Then there's the possibility of dark radiation, an invisible, relativistic component that could have influenced the early universe's expansion, leaving a fingerprint in today's tension. Think of it like a hidden ingredient in a recipe that changes how the dish turns out. If dark radiation existed, it would have affected the cosmic microwave background in a way that tweaks our predictions, potentially bridging the gap between the conflicting measurements. But the plot thickens further. Another angle considers whether dark matter and dark energy, the mysterious force accelerating the universe's expansion, might be linked. Could dark matter decay into dark energy over time, or vice versa? Such an interaction would rewrite the rules of cosmic evolution, explaining why our expansion rate measurements don't align. It's a radical idea, but in the hunt for answers, no stone can be left unturned. The stakes here are enormous. If the Hubble tension points to new physics involving dark matter, it would upend our understanding of the universe's fundamental workings. Future telescopes like the Nancy Grace Roman Space Telescope aim to measure the expansion rate with unprecedented precision, potentially uncovering clues hidden in the large-scale structure of the cosmos. Until then, the Hubble tension remains a cosmic tug-of-war, one where dark matter might just be the invisible hand tipping the scales. As we untangle the web of cosmic mysteries, let's journey back to the dawn of time, where the first stars might have burned with an entirely different kind of fire. Picture this: colossal, dimly glowing orbs, not fueled by nuclear fusion like today's stars, but by the annihilation of dark matter itself. These are dark stars, one of the most tantalizing what-ifs in modern astrophysics. The concept flips stellar evolution on its head. Normally, stars shine because hydrogen atoms smash together in their cores, releasing energy through fusion. But dark stars would operate on a different principle. In the early universe, dense clouds of hydrogen and helium could have trapped vast amounts of dark matter. If those dark matter particles collided and annihilated, converting their mass into heat, they might have powered stars without fusion ever igniting. The result: behemoths hundreds of times more massive than our Sun, glowing faintly with a cool, eerie light, and lasting far longer than conventional stars. Here's where it gets even wilder. Dark stars wouldn't just be oddities, they could solve lingering puzzles about the early cosmos. For instance, some supermassive black holes in the young universe are too big to explain under current models. If dark stars existed, their sheer size could have collapsed directly into black holes, seeding these early giants. They might also explain why certain ancient galaxies appear brighter than expected. Their light could be boosted by lingering dark stars lurking within them. Now enter the James Webb Space Telescope, our most powerful window into the primordial universe. JWST infrared eyes are perfectly tuned to spot the faint, redshifted glow of the earliest stars and galaxies. If dark stars are out there, they'd emit a distinct thermal signature, warmer than the cosmic background but cooler than fusion-powered stars. JWST could detect this fingerprint, especially if these objects are magnified by gravitational lensing. Already, astronomers are scouring JWST deep field images for unusually red, diffuse objects that don't quite fit the mold of ordinary stars or galaxies. Of course, the hunt is riddled with challenges. Dark stars would be incredibly rare today, and their faint light could easily be mistaken for distant galaxies. Plus, their existence hinges on specific properties of dark matter, like its ability to annihilate efficiently. If dark matter turns out to be more inert, dark stars might remain forever hypothetical. But that's the thrill of cosmology. Every new telescope brings us closer to testing ideas that once seemed like pure speculation. So keep an eye on JWST discoveries. If we're lucky, it might just spot the ghostly glow of a dark star, a relic from a time when the universe burned with a hidden, mysterious flame. And if it does, the implications would be staggering, rewriting not just the story of stars, but the very nature of dark matter itself. Now let's shift our gaze to one of the most puzzling behaviors in the cosmos, an enigma so strange that astronomers call it the dark flow. Picture hundreds of galaxy clusters, each containing thousands of galaxies, all streaming through space in the same direction at staggering speeds of nearly 2 million miles per hour. This isn't random motion. It's as if some immense, invisible force is pulling them toward a point beyond the edge of our observable universe. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Scientists expected galaxy clusters to move randomly, their motions balancing out like leaves drifting on a pond. But when they analyzed data from hundreds of clusters, they found something unsettling: a coordinated movement toward the constellations Centaurus and Hydra. This directional rush defies everything we know about cosmic expansion, which should scatter matter evenly in all directions. Here's where dark matter enters the mystery. One leading theory suggests these clusters are being towed by colossal structures made of dark matter, cosmic filaments so vast they stretch beyond our horizon. Imagine a gigantic cosmic web with threads denser and more massive than anything we've mapped. If such structures exist, their gravity could be tugging entire clusters like puppets on strings. Another possibility, the gravitational pull of a neighboring universe, a mind-bending idea that pushes the limits of cosmology. But dark flow isn't without controversy. Some researchers argue it might be an illusion caused by incomplete data or measurement errors. others point out that even dark matter's gravity shouldn't create such coherent motion across billions of light years. The debate grew so heated that when the Planck satellite's findings failed to confirm the signal definitively, many dismissed it as a statistical fluke. Yet tantalizing clues remain. Recent studies of superclusters, the universe's largest bound structures, still show subtle hints of this mysterious flow. What makes dark flow so revolutionary is its potential to upend our cosmic maps. If real, it implies that something enormous, something beyond our sight, is warping the universe on scales we can't comprehend. It challenges the cosmological principle, the foundational idea that the universe looks roughly the same in all directions. And if dark matter is behind it, we might need to rethink its distribution or even its fundamental properties. For now, the dark flow remains one of astrophysics' great open questions. Future telescopes, like the European Space Agency's Euclid mission, could settle the debate by mapping dark matter's influence with unprecedented precision. Until then, this cosmic river of galaxies serves as a humbling reminder. The universe still holds forces darker, stranger, and more powerful than we've dared to imagine. Now let's turn our attention to one of the most intense cosmic relationships, dark matter and black holes. These two mysteries of the universe might be more connected than we ever imagined. Could dark matter be the invisible fuel that feeds supermassive black holes at the centers of galaxies? Or is it possible that dark matter itself is made of ancient black holes, remnants from the dawn of time? Take a closer look at the supermassive black holes lurking in galactic cores. These cosmic monsters weigh millions, even billions of times more than our Sun. But here's the puzzle: how did they grow so large so quickly? Some astronomers think dark matter might be the answer. As dark matter particles collide and annihilate near a black hole's event horizon, they could release bursts of energy, effectively feeding the beast. Others suggest dark matter's gravity might funnel regular matter into the black hole, supercharging its growth. Imagine dark matter as an invisible conveyor belt, shoveling gas and stars toward an insatiable maw. Then there's the wilder idea that dark matter isn't just interacting with black holes, but that some black holes are dark matter. Primordial black holes, hypothetical objects thought to have formed in the chaos of the early universe, could fit the bill. Unlike the black holes we know, born from collapsing stars, these would be relics from the first fractions of a second after the Big Bang. If they exist in vast numbers, too small and cold to emit detectable radiation, they might collectively account for the missing mass we call dark matter. This theory isn't without challenges, though. Primordial black holes would need to form in just the right sizes, not too big, not too small, to match dark matter's behavior. Too massive, and their gravity would distort galaxies in ways we don't observe. Too light, and they'd have evaporated by now due to Hawking radiation. Yet tantalizing clues persist. Some gravitational wave signals from colliding black holes hint at objects that might fit this primordial profile, sparking fresh debate. The stakes couldn't be higher. If primordial black holes are dark matter, it would rewrite our understanding of both. It would mean dark matter isn't an exotic particle but a population of ancient black holes lurking unseen in the cosmic shadows. Alternatively, if dark matter fuels supermassive black holes, it would reveal a hidden mechanism shaping galaxies from within. Future observations might tip the scales. Telescopes like the Laser Interferometer Space Antenna, or LISA, could detect the faint ripples from primordial black hole collisions. Meanwhile, studies of how supermassive black holes grow could uncover dark matter's feeding patterns. Either way, this cosmic detective story reminds us that the universe's greatest mysteries might be hiding in plain sight, or just beyond the event horizon. Now let's shift our gaze to the empty spaces, the vast cosmic voids where dark matter seems to take a step back, leaving behind a haunting emptiness. These voids, sprawling across millions of light-years, aren't just empty patches of the universe, they're critical pieces of the cosmic puzzle, revealing what happens when dark matter's grip weakens. Picture the universe as a sponge, with galaxies clustered along its dense filaments and sheets. The holes in that sponge, those are the voids, regions so empty that some contain only a handful of galaxies. But here's the twist: even in these near-vacant spaces, dark matter's influence doesn't vanish entirely. Instead, it's stretched thin, like a ghostly web with its threads pulled apart. This scarcity of dark matter in voids creates a unique laboratory for testing our theories. Without the usual gravitational scaffolding, galaxies inside voids evolved differently, often smaller, quieter, and slower to form stars compared to their crowded cousins in galaxy clusters. One of the biggest surprises is how these voids challenge our models of cosmic structure. Simulations predict that voids should grow over time as dark matter and galaxies migrate toward denser regions, leaving emptiness behind. But observations show some voids are too empty, more extreme than simulations suggest. This mismatch hints that dark matter might behave oddly in these regions, or that we're missing a key ingredient in our theories. Some researchers even propose that dark energy, the mysterious force accelerating the universe's expansion, could be playing a stronger role in voids, pushing them to grow faster than expected. Then there's the curious case of void galaxies. These lonely objects adrift in the cosmic wilderness often appear younger and bluer than their counterparts in denser regions. Without the relentless gravitational tug of war found in clusters, void galaxies experience a quieter life with fewer collisions and mergers. But their isolation comes at a cost. They're starved of the fresh gas that fuels star formation, leading to a slower, more stagnant evolution. Studying these galaxies is like watching a tree grow in the desert, stunted, yet revealing secrets about the harsh environment around it. The real intrigue lies in what voids tell us about dark matter's nature. If dark matter particles interact with each other not just through gravity but via some unknown force, voids could be where these interactions become visible. For example, if dark matter particles collide and scatter, they might avoid piling up in voids as much as expected, explaining their puzzling emptiness. Experiments like the Dark Energy Survey are mapping voids in unprecedented detail, searching for these subtle clues. But voids aren't just passive windows, they're active shapers of the cosmic web. Their expansion creates pressure, squeezing surrounding filaments and sheets, which in turn affects how galaxies form and move. It's a cosmic domino effect. Empty regions push matter into denser structures, accelerating the birth of galaxy clusters and superclusters. This feedback loop means that understanding voids isn't just about studying absence, it's about seeing how emptiness drives the universe's richest structures. The next frontier, peering into the earliest voids with telescopes like the James Webb Space Telescope, which could spot the faintest galaxies in these regions, tracing how voids evolved over billions of years. If we can unravel why voids are so empty and how dark matter's absence sculpts them, we might finally unlock one of cosmology's most enduring questions: how the universe's invisible skeleton shapes everything we see. Up next, we'll dive into one of dark matter's most contentious debates, a signal detected deep underground that some claim is dark matter's long-awaited whisper, while others dismiss it as mere background noise. What's really going on with the DAMA experiment? That's where we're headed. Turning our attention from the vast emptiness of cosmic voids, we arrive at one of dark matter's most heated debates, a signal buried deep underground in an Italian mountain, sparking decades of controversy. The DAMA experiment, nestled beneath the Gran Sasso Massif, claims to have detected a flicker of dark matter, but the scientific community remains sharply divided. Why? Because no other detector on Earth has been able to replicate its peculiar findings. At the heart of the mystery is an annual wiggle in DAMA data, a rhythmic signal that peaks every June and dips in December. The team behind the experiment argues this pattern matches exactly what we'd expect if dark matter particles were streaming through Earth. Here's why: as our planet orbits the Sun, it moves through the Milky Way's dark matter halo, which should create a wind of particles. In June, Earth's motion adds to the Sun's movement through the galaxy, making the apparent wind stronger. By December, Earth is moving against the Sun's direction, so the wind seems weaker. This seasonal dance, Dama claims, is dark matter's calling card. The experiment uses sodium iodide crystals as its detectors. When a particle like dark matter bumps into an atomic nucleus in these crystals, it should produce a tiny flash of light. Dama has observed these flashes for over 2 decades, insisting the annual modulation can't be explained by background noise or known particles. But skeptics point to a glaring issue. Other experiments like Xenon and Lux, which use different materials and methods, haven't seen anything resembling Dama's signal. Critics suggest mundane explanations. Could the modulation come from seasonal changes in the lab's environment, temperature shifts, humidity, or even cosmic ray variations? Dama team has rigorously ruled these out, but the doubt lingers. Another wrinkle is the type of dark matter Dama might be seeing. Most experiments hunt for WIMP-heavy, sluggish particles, but Dama's signal could hint at lighter, faster particles that other detectors aren't optimized to catch. This has led some to speculate about alternative dark matter candidates, like mirror matter or particles interacting via an unknown force. The plot thickened when Dama upgraded to Libra, a more sensitive version of the experiment, and the signal persisted. Yet, even with this consistency, the lack of independent confirmation keeps the debate alive. Newer experiments like Cosine and Anise, also using sodium iodide, initially seemed to contradict Dama, but their results weren't conclusive enough to settle the matter. Meanwhile, theorists keep tweaking models to explain why Dama might be seeing something others aren't, exploring ideas like dark matter with asymmetric interactions or exotic nuclear effects in sodium iodide. What makes this controversy so gripping is its stakes. If Dama is right, it's the first direct detection of dark matter in human history, a Nobel-worthy breakthrough. If it's wrong, it's a cautionary tale about how easily patterns in data can deceive us. Either way, the puzzle pushes scientists to refine their methods and question assumptions. Up next, we'll venture into the quantum realm, where dark matter might not just be invisible, it could be operating by rules that defy our current understanding of physics. What happens when dark matter meets quantum weirdness? That's where we're headed next. Now let's take a sharp turn into the bizarre world of quantum mechanics, where dark matter might not just be hiding, it could be playing by entirely different rules. Imagine particles that don't just pass through walls but exist in multiple states at once, or vanish and reappear unpredictably. This isn't science fiction. It's the frontier of dark matter research, where scientists are probing whether its secrets are tied to the mind-bending laws of the quantum realm. One tantalizing idea is that dark matter could be made of actions hypothetical particles so light and slippery they behave more like waves than solid objects. Actions were originally proposed to solve a puzzle in particle physics unrelated to dark matter, but their ghostly nature makes them perfect candidates. Here's where quantum weirdness kicks in. Actions might couple to photons, meaning they could transform into light particles in the presence of strong magnetic fields. Experiments like ADMS are essentially giant radio receivers tuned to detect this faint, telltale static from action conversions. Picture turning a dial slowly, waiting for a blip of sound in a sea of silence. That's the painstaking hunt for actions. But the quantum connection doesn't stop there. Sterile neutrinos, cousins of the nearly massless neutrinos we know, could also be dark matter. Unlike regular neutrinos, which interact via the weak nuclear force, sterile neutrinos would feel only gravity, making them utterly invisible. Yet quantum mechanics allows them to oscillate or morph into detectable neutrinos, leaving subtle imprints in X-ray emissions from distant galaxies. A mysterious line of X-rays spotted from galaxy clusters, nicknamed the 3.5 kilo electronvolt line, might be the decay signature of sterile neutrinos. It's like catching the shadow of a creature that can't be seen directly. Then there's the possibility that dark matter isn't just influenced by quantum rules, it might exploit them in ways we've never imagined. Some theories suggest dark matter particles could be entangled across vast cosmic distances, instantly affecting one another like quantum twins. If true, this would mean dark matter forms an invisible, interconnected web that responds as a single entity, defying classical physics. Others speculate dark matter might have superposition, existing in multiple places at once until an interaction forces it to choose a state. This could explain why it's so hard to pin down. Every time we try to observe it, the act of observation itself might alter its behavior. The wildest proposals even link dark matter to quantum black holes or extra-dimensional particles that flicker in and out of our reality. String theory, for instance, suggests dark matter could be a vibration in higher dimensions, a cosmic hum we can't hear but whose gravity tugs on our universe. These ideas aren't just speculative, they're testable. Gravitational wave detectors might pick up ripples from primordial black hole collisions, while quantum lab experiments could uncover hidden particles tunneling through barriers. What makes this intersection of dark matter and quantum mechanics so thrilling is its potential to rewrite physics. If dark matter operates on quantum principles we've yet to grasp, discovering them could unlock everything from new energy sources to insights about the birth of the universe. But for now, it's a puzzle wrapped in uncertainty, one that keeps physicists awake at night, chasing whispers in the quantum dark. Up next, we'll tackle an equally perplexing riddle: why our galaxy seems to have far fewer satellite galaxies than dark matter theory predicts. Is the universe playing hide and seek, or is our understanding of cosmic structure missing a crucial piece? Now let's shift our gaze closer to home, to a cosmic head-scratcher unfolding right in our galactic backyard. If dark matter is the universe's invisible scaffolding, then dwarf galaxies' tiny, dim collections of stars should be swarming around the Milky Way like bees around a hive. But here's the twist: while supercomputer simulations predict thousands of these satellite galaxies, telescopes spot only a few dozen. This glaring mismatch, known as the missing satellites problem, has astronomers questioning whether dark matter's behavior might be stranger than we thought. To understand why this discrepancy matters, picture dark matter as a cosmic glue. After the Big Bang, it clumped together under gravity, forming halos that pulled in gas to birth stars and galaxies. Simulations like Via Lactea and Aquarius show these halos should spawn countless dwarf galaxies around larger ones like the Milky Way. Yet when we scan our skies, the numbers don't add up. Some of these missing dwarfs might simply be too faint to detect. Imagine trying to spot fireflies against a city's glare. But even accounting for observational limits, the gap persists. Could dark matter be misbehaving? One leading fix is the idea that early cosmic radiation, a searing bath of ultraviolet light from the first stars, might have sterilized small halos, stripping away their gas before stars could form. Without fuel, these halos would remain dark and invisible, explaining the shortage of visible dwarfs. This reionization scenario has merit, but it doesn't fully close the gap. Another twist comes from the dwarfs we do see, like Draco and Ursa Minor. These galaxies are freakishly rich in dark matter, up to 1,000 times more than their starlight suggests. If typical, this imbalance implies most dwarfs are just too dim to spot, lurking as dark galaxies with almost no stars at all. Then there's the too big to fail problem. The Milky Way's most massive dark matter subhalos seem empty. Where are the giant dwarf galaxies they should host? Some argue feedback from supernova blew out their gas, while others suspect these halos were shredded by the Milky Way's tides. But critics counter that even disrupted halos should leave trails of stars, which we rarely find. This has led to radical rethinks like tweaking dark matter's properties. If it's warm, moving faster than cold dark matter, it would smear out small halos, reducing dwarf counts. Alternatively, dark matter might interact with itself, scattering particles and smoothing halos into invisibility. The plot thickens with the discovery of ultra-faint dwarfs like Segway 1, which has just a handful of stars but a monstrous dark matter core. These ghosts hint that the missing satellites might be hiding in plain sight, too dim for older surveys but detectable with tools like the Vera Rubin Observatory. Meanwhile, the Gaia spacecraft is mapping stellar streams, remnants of dwarfs torn apart by our galaxy's gravity. Each shredded galaxy is a clue revealing how dark matter shaped and continues to shape the Milky Way's evolution. The satellite puzzle isn't just academic, it's a stress test for cosmology. If simulations and reality can't reconcile, does dark matter need a rewrite, or are we underestimating the chaos of galaxy formation? As telescopes peer deeper, the answer might lie in the shadows, not just of missing dwarfs, but of the invisible rules governing them. Up next, we'll venture into an even more enigmatic idea, that dark matter's secrets might be tangled with the very fabric of time itself. Could clocks tick differently in a dark matter universe? Stay with us as we unravel this temporal twist. Now let's step into one of the most mind-bending corners of dark matter research, a realm where the invisible stuff might not just shape space but time itself. Picture this: what if dark matter doesn't just lurk unseen, but also bends the rules of how clocks tick? It sounds like science fiction, but anomalies like the bizarre galaxy NGC 1052 DF2 are forcing scientists to consider exactly that. This so-called double galaxy defies expectations. It's nearly devoid of dark matter, yet it moves too slowly for its visible mass alone. Normally, galaxies with less dark matter should zip around faster, like a spinning ice skater pulling their arms in. But DF2 drags its feet, as if some unseen hand is slowing time in its vicinity. Could dark matter's absence here actually alter how gravity and time operates? The implications are staggering. If dark matter interacts with time differently, it might explain other cosmic oddities, like why some galaxies seem to evolve faster or slower than their peers. Einstein's theory of relativity already tells us time isn't universal. Clocks tick slower near massive objects like black holes, but dark matter's time-bending potential would take this further. Imagine regions of space where dark matter is dense. Time might flow differently there, subtly skewing how galaxies age or how light reaches us across billions of years. This could even help solve the Hubble tension, the nagging discrepancy in the universe's expansion rate. If dark matter's influence on time varies across cosmic history, it might reconcile conflicting measurements of how fast space is stretching. Then there's the time dilation puzzle in galaxy clusters. Some studies suggest clocks in these dark matter-rich environments run slightly off-sync compared to emptier voids. The difference is tiny nanoseconds over millennia, but if real, it hints that dark matter doesn't just warp space with gravity, it might warp space-time itself. Leading theories propose that dark matter particles could have unique couplings to the fundamental fields that govern time, akin to how magnets interact with magnetic fields. Of course, skeptics argue these anomalies could stem from measurement errors or overlooked astrophysics, but the stakes are high. If dark matter and time are entangled, it would rewrite our understanding of reality's fabric. Up next, we'll dive into another radical idea, that dark matter might be hiding in plain sight because it's governed by a mysterious dark photon force, a hidden cosmic glue unlike anything we've seen. Stay tuned as we explore the frontier where particle physics meets the unknown. Now let's shift our gaze to a groundbreaking idea that could rewrite the rules of how dark matter interacts with the cosmos, the hunt for the so-called dark photon. Imagine if dark matter doesn't just sit silently in the shadows, but actually communicates through its own hidden force. mediated by a mysterious particle unlike anything in our standard model. This is the essence of the dark photon hypothesis, a tantalizing possibility that's sending physicists on a high-stakes treasure hunt. Think of it like this: just as photons carry the electromagnetic force between particles we can see, dark photons might be the invisible messengers for dark matter, enabling it to interact with itself, or even subtly with ordinary matter. The implications are staggering. If dark photons exist, they could explain why dark matter seems to cluster in halos around galaxies while avoiding direct detection. It might also solve puzzling anomalies, like why some experiments catch faint, unexpected signals that vanish upon closer inspection. One of the most compelling clues comes from particle colliders. Experiments like the Large Hadron Collider have scoured their data for traces of dark photons, looking for energy that mysteriously disappears, a potential signature of these ghostly particles slipping undetected into the dark sector. Then there's the ingenious approach of lab-based experiments like dark light and HPS, which blast ordinary electrons into targets, hoping to spot the rare moment a dark photon is born and quickly decays. These setups are like cosmic fishing nets, designed to trap the slightest whisper of dark sector activity. But here's where it gets even stranger. Some theories suggest dark photons could have a tiny amount of mass, unlike their massless standard model cousins. This massive photon idea opens wild possibilities, like dark photons acting as a bridge between dark matter and ordinary particles. Picture a scenario where dark matter occasionally shakes hands with visible matter through these elusive intermediaries, leaving behind faint fingerprints in the form of anomalous magnetic fields or unexpected energy shifts in atomic transitions. Critics, of course, urge caution. No experiment has definitively snagged a dark photon yet, and alternative explanations, like unknown astrophysical processes, could account for the anomalies. But the hunt is far from over. Projects like Phaser at the LHC and proposed future colliders are refining their search strategies, targeting specific energy ranges where dark photons might hide. Meanwhile, astrophysicists scour cosmic phenomena like the precise cooling of stars or the behavior of supernova remnants for irregularities that could hint at dark photon interactions. What makes this search so thrilling is its duality. On one hand, dark photons could be the key to unlocking dark matter's secrets. On the other, they might open a portal to an entire shadow universe, complete with its own forces and particles. Up next, we'll journey back to the dawn of time to explore how dark matter might have first emerged in the primordial chaos of the early universe, a story written in the faint echoes of the Big Bang itself. To peel back another layer of this cosmic mystery, let's travel back to the very beginning where dark matter itself may have first stirred into existence. Picture the universe in its infancy, a seething cauldron of energy mere fractions of a second after the Big Bang. In this primordial chaos, the seeds of dark matter were likely sown, not through the familiar processes that forged stars and galaxies, but through quantum whispers in the fabric of spacetime itself. One leading theory suggests dark matter emerged during cosmic inflation, that brief but exponential expansion of the universe before it was even a second old. Tiny quantum fluctuations during this period, ripples in energy density, may have stretched to cosmic scales, later collapsing under gravity to form the first dark matter structures. Think of it like stretching a crumpled sheet of paper. The microscopic wrinkles become vast valleys and ridges, invisible scaffolding for the universe to be. These fluctuations weren't just random noise. They carried the blueprint for everything, including the dark matter web we see mapped in modern galaxy surveys. Then came the phase transitions. As the newborn universe cooled, it underwent dramatic shifts in its fundamental state, like water freezing into ice. And these moments may have birthed dark matter particles en masse. Some models propose a scenario akin to condensation, where certain particles suddenly fell out of the hot plasma, becoming dark matter. Others suggest a more violent origin, bubbles of new physics forming and colliding in the early universe, releasing showers of dark matter as they popped. The key clue, the cosmic microwave background. Its subtle temperature variations hold fingerprints of these ancient upheavals, with patterns that suggest dark matter was already shaping the cosmos just 380,000 years after the Big Bang. Intriguingly, the timing of dark matter's formation could explain its ghostly nature. If it decoupled from ordinary matter before the universe was a picosecond old, before even quarks and gluons had settled into protons, it would have missed the party where all known forces and particles established their rules. This isolation might be why dark matter now refuses to interact via electromagnetism or the strong nuclear force. It's not being shy, it's playing by a different rulebook written in the universe's first heartbeat. But the plot thickens with competing origin stories. Could dark matter be relics of extra dimensions predicted by string theory, or leftovers from a hidden sector of particles that briefly flickered into existence? Some physicists even explore the idea of asymmetric dark matter, where an imbalance in dark particle production, like the matter-antimatter asymmetry we see in the visible universe, left behind a surplus that became today's cosmic shadow. The hunt for answers now hinges on particle accelerators recreating extreme early universe conditions, and telescopes like the James Webb peering back to epochs when the first dark matter halos were assembling. What's breathtaking is how these primordial whispers still echo today. When galaxies spin too fast or clusters bend light strangely, we're glimpsing the aftermath of events that unfolded when time itself was still learning to tick. Next, we'll confront an even bolder idea, that dark matter might be tied to a fifth force of nature, one that quietly sculpts the cosmos behind gravity's back. Now let's push the boundaries even further and consider a radical idea. What if dark matter isn't just governed by gravity alone? Imagine a hidden force, something beyond the four we know: gravity, electromagnetism, and the strong and weak nuclear forces quietly pulling the strings in the cosmos. This is the tantalizing possibility of a fifth force, one that could rewrite our understanding of how dark matter shapes the universe. Think of it like this: gravity is the architect of the cosmic web, but what if dark matter has its own secret toolkit? Some theories suggest dark matter particles interact with each other through an entirely new force, separate from the ones that govern ordinary matter. This wouldn't just be a minor tweak to physics, it could explain puzzling behaviors in galaxy clusters where gravity alone doesn't quite add up. For instance, in the famous Bullet Cluster, where two galaxy clusters collided, dark matter appears to have sailed smoothly through the chaos while ordinary gas slowed down. If dark matter had an extra force at play, perhaps a kind of dark electromagnetism, it might explain why it behaves so differently. But how would this fifth force work? One leading idea involves a hypothetical dark photon, a particle that could act as a messenger for this new force, much like photons carry electromagnetic energy. Experiments like the Large Hadron Collider and specialized detectors are hunting for traces of these phantom particles. If they exist, dark photons could mediate interactions between dark matter particles, creating subtle but measurable effects, like slight deviations in how galaxies move within clusters or unexpected distortions in cosmic structure. Here's where things get even stranger. Some models propose that this fifth force could have a limited range, only affecting dark matter on small scales, say within a single galaxy. This might explain why dwarf galaxies, which should be packed with dark matter according to simulations, sometimes appear less dense than expected. If dark matter particles push each other apart via this force, they'd spread out more, diluting their gravitational grip. It's like adding an invisible repulsion to the mix, tweaking the rules just enough to match observations. Critics, of course, argue that modifying gravity, like in Mond theories, could explain these anomalies without invoking a fifth force. But here's the catch: certain cosmic structures, like the intricate filaments of the dark matter web, seem too finely woven for gravity alone to have crafted them. A fifth force could provide the extra sculpting power needed, acting like an unseen hand guiding dark matter into place. The implications are staggering. If confirmed, a fifth force would mean dark matter isn't just a passive spectator. It's an active player with its own hidden physics. Upcoming telescopes like Euclid and Vera Rubin Observatory could spot telltale signs in the way galaxy clusters evolve, while underground experiments might catch dark photons in action. Either way, the hunt for this phantom force is forcing us to rethink the very fabric of reality. And this brings us to an even wilder twist. What if dark matter's secrets are buried not just in new forces, but in other dimensions entirely? That's a mystery we'll unravel next. Now let's stretch our imaginations even further. What if dark matter isn't just hiding in plain sight, but lurking in dimensions we can't perceive? This isn't science fiction. String theory, one of the most ambitious frameworks in physics, suggests our universe might have more than the 3 spatial dimensions we experience every day. Extra dimensions could be curled up so tightly that they're invisible to us, like the folds of a crumpled piece of paper. And here's the twist: dark matter might be tapping into these hidden realms, which would explain why it's so stubbornly undetectable. Think of it this way: if dark matter particles exist in higher dimensions, they could be right beside us, but leaking gravity into our familiar 3-dimensional space. That would explain why we feel dark matter's gravitational pull but can't see or touch it. It's like a shadow cast by an object in another dimension, visible only by its effect. This idea isn't just speculative math. Experiments hunting for gravitational waves like LIGO and Virgo might hold clues. If dark matter interacts with these hidden dimensions, it could leave faint fingerprints in the ripples of space-time anomalies that don't match predictions from general relativity. One tantalizing possibility involves brain-world models, where our universe is a 3-dimensional brain floating in a higher dimensional space. Ordinary matter and forces like electromagnetism are stuck to our brain, but gravity and potentially dark matter can seep into the extra dimensions. This could explain why gravity is so much weaker than other forces. And if dark matter is a higher dimensional traveler, it might occasionally bump into our brain, creating odd gravitational effects. For instance, certain patterns in the cosmic microwave background or unexplained gaps in gravitational wave data could hint at these collisions. But how do we test something so abstract? Scientists are getting creative. Some propose that if dark matter particles are heavy enough, their movements in extra dimensions could generate high-frequency gravitational waves, ripples too subtle for current detectors but potentially within reach of future observatories like LISA or the Einstein telescope. Others suggest looking for distortions in the orbits of stars near the Milky Way center, where a higher dimensional dark matter halo might warp space-time in unexpected ways. Here's where it gets even wilder. If dark matter is truly multidimensional, it might not be a single particle but a spectrum of higher dimensional objects, strings, membranes, or even black holes from other dimensions. Some theories suggest primordial black holes formed in the early universe could be dark matter candidates if they're hiding in these extra dimensions. Their gravity would still leak into our world, but their small size and higher dimensional anchoring would make them nearly impossible to spot directly. Critics argue that extra dimensions are untestable poetry, but defenders counter that math doesn't lie. The equations predict measurable anomalies, and if future gravity wave detectors or precision astrophysical measurements find discrepancies, we might have our first proof of a multidimensional cosmos. Imagine the implications. Dark matter wouldn't just be invisible matter, it'd be a gateway to understanding the full architecture of reality, hidden layers woven into the fabric of space itself. This brings us to an even more mind-bending question. What if dark matter isn't just in another dimension, but part of an entirely separate universe? That's a mystery we'll explore next. Now let's take a leap into one of the most radical ideas in modern cosmology, the mirror universe theory. Picture this. What if dark matter isn't just an elusive particle or a higher dimensional ghost, but ordinary matter from a parallel reality, one with slightly different laws of physics? This isn't just a sci-fi plot twist. Serious physicists have explored the idea that our universe might have a hidden twin, a mirror world where particles interact differently, making them invisible to us except through gravity. Here's how it could work. Imagine a mirror universe almost identical to ours, with its own stars, galaxies, and even planets. But in that world, the fundamental forces like electromagnetism or the strong nuclear force behave differently. Because of this, their matter doesn't emit, absorb, or reflect light the way ours does. To us, it's completely dark. The only way these two universes talk to each other is through gravity, which leaks across the divide. That's why we feel the pull of dark matter but can't see it. It's not missing. It's just part of a reality operating by different rules. This idea isn't as far-fetched as it sounds. Symmetry is a cornerstone of physics, and nature loves to mirror itself. Take neutrinos, for example. These particles come in left-handed versions that interact via the weak force, but no known right-handed ones exist in our universe. Some theories suggest those missing right-handed neutrinos could be hiding in a mirror world, where they're just as common as our ordinary matter. If true, these mirror neutrinos could be part of dark matter's identity particles we've been searching for all along, just in the wrong universe. But how would a mirror universe even form? One possibility is that during the Big Bang, space-time didn't just expand, it split. Think of it like a tree branching into two trunks. Both universes share the same origin but evolve independently, each with its own version of particles and forces. In our twin, protons might be slightly heavier or electromagnetism weaker, altering how matter behaves. This could explain why dark matter halos around galaxies are so diffuse. They're not clumpy like our matter because their physics prevents them from collapsing into dense structures. Now here's where it gets fascinating. If a mirror universe exists, it might not just be a passive shadow. Some models suggest that early in cosmic history, the two realms could have briefly interacted, leaving imprints in the cosmic microwave background, those faint afterglow patterns from the Big Bang. Certain anomalies in the CMB, like unexpected cold spots or uneven distributions of matter, might be scars from this ancient crossover. Future telescopes, like the European Space Agency's Euclid mission, could hunt for these fingerprints, turning speculation into evidence. Critics argue that mirror matter is untestable by definition. If it doesn't interact with our world except via gravity, how do we prove it's there? But supporters counter that even subtle differences in how dark matter behaves could hint at its mirror nature. For instance, if dark matter halos around galaxies are smoother or more evenly distributed than predicted, that might reflect the alternate physics of their home universe. And here's the kicker: if mirror matter exists, it could mean life, or something like it exists over there too. A mirror universe might have its own chemistry, planets, even civilizations, all built from atoms that don't interact with ours. We'd never see their light or hear their signals, but their gravity would silently shape the cosmos we observe. It's a humbling thought. The stuff we call dark matter could be someone else's ordinary reality, just out of reach. So where does this leave us? The mirror universe theory stretches our imagination, blurring the line between science and speculation. But in a puzzle as deep as dark matter, sometimes the wildest ideas are the ones worth exploring. After all, the universe has surprised us before. Why wouldn't it hide its greatest secrets in plain sight, just beyond the mirror? Now let's shift our focus to something even more ethereal, the idea that dark matter might be humming a cosmic tune. Picture the universe not just as a silent, empty void, but as a vast orchestra with dark matter producing vibrations so subtle we've only just begun to detect them. These aren't ordinary sounds, of course, but ripples in space-time itself, gravitational waves. And what if some of the faintest, lowest frequency gravitational waves we've detected aren't from colliding black holes or neutron stars, but from dark matter itself? This theory hinges on the possibility that dark matter isn't completely inert. Some models suggest certain types of dark matter particles, like actions or even primordial black holes, could vibrate or oscillate as they move through space. Think of it like a tuning fork struck in a vacuum. No sound travels, but the vibrations still exist. Over colossal distances and timescales, these tiny oscillations might add up, creating a faint, universe-wide hum detectable as low-frequency gravitational waves. The catch: these waves would be incredibly subtle. The gravitational waves we've observed so far, like those from LIGO and Virgo, are the cosmic equivalent of cymbals crashing, loud, brief bursts from violent collisions. But the hum we're talking about would be more like the deepest note on a pipe organ, resonating for billions of years. Detecting it requires instruments sensitive enough to pick up shifts smaller than the width of an atom across distances longer than our solar system. That's where projects like LISA come in. The Laser Interferometer Space Antenna, set to launch in the 2030, will float 3 spacecraft millions of kilometers apart, using lasers to measure space-time ripples with unparalleled precision. Unlike ground-based detectors, LISA won't be rattled by Earth's noise, making it ideal for hunting these ultra-low-frequency waves. If dark matter truly hums, LISA could be the first to hear it. But why would dark matter vibrate in the first place? One compelling idea involves actions hypothetical particles that are leading candidates for dark matter. Actions are thought to behave less like discrete particles and more like a pervasive, wave-like field permeating space. Under the right conditions, this field could oscillate, creating ripples in spacetime. Another possibility involves vast clouds of primordial black holes, the smallest of which might evaporate over time via Hawking radiation, producing faint gravitational whispers as they fade. The implications are staggering. If we could tune into this cosmic hum, it wouldn't just confirm the existence of dark matter, it could reveal its nature. Different dark matter particles would sing at different frequencies. Actions might produce a smooth, continuous tone, while primordial black holes could generate a chorus of irregular pulses. Matching these signals to predictions would be like identifying a composer by their musical style. There's already tantalizing, if controversial, evidence. Some researchers argue that anomalies in pulsar timing arrays networks of ultra-precise cosmic clocks might hint at a background hum of gravitational waves. Others suggest peculiar distortions in the cosmic microwave background could be echoes of dark matter vibrations from the early universe. These claims are far from confirmed, but they've ignited a race to refine our detectors and models. Critics point out that attributing these signals to dark matter is speculative. The hum could come from other sources, like merging supermassive black holes or cosmic strings, hypothetical defects in spacetime. But proponents counter that dark matter's omnipresence makes it a prime suspect. After all, if it's everywhere, its vibrations should be too, woven into the fabric of the universe. What's truly mind-bending is the scale of this idea. If dark matter hums, it means the universe isn't just filled with invisible mass, it's alive with imperceptible motion, a symphony of vibrations shaping galaxies and bending spacetime. Future experiments might not just solve the dark matter puzzle, but open an entirely new way to listen to the cosmos. And if we're lucky, the universe's quietest song could reveal its deepest secrets. So keep your ears open, figuratively of course. The next great discovery in astrophysics might not be something we see, but something we feel, as the universe's dark heart beats in waves we're only beginning to sense. Now, let's step into the final frontier of this cosmic puzzle, the big question looming over every dark matter mystery. Will we ever truly solve it? After all, we've spent decades chasing shadows in the universe, building detectors the size of buildings, launching telescopes into space, and still, dark matter refuses to reveal itself directly. So where does that leave us? Are we on the brink of a breakthrough, or is dark matter destined to remain an eternal enigma? The answer, like dark matter itself, is shrouded in uncertainty, but there's reason for both hope and humility. On one hand, the next generation of experiments and missions could finally crack the case. Take LISA, the gravitational wave observatory we mentioned earlier. By the 2030s, it'll scan the cosmos for ripples in spacetime with such precision that it might catch dark matter humming. Then there's Euclid, the European Space Agency's dark matter hunter, set to map the distribution of galaxies and dark matter across 10 billion light-years. Euclid won't just look for dark matter's gravitational fingerprint. It could expose how dark energy, its even more mysterious counterpart, interacts with it. But it's not just about space telescopes. Underground labs are pushing the limits too. The LZ experiment in South Dakota and Xenon NT in Italy are scaling up their detectors to catch even the faintest whispers of dark matter particles. Meanwhile, particle colliders like the upgraded Large Hadron Collider might smash protons together at energies high enough to create dark matter in the lab. These efforts are like assembling a cosmic net, each strand woven tighter to catch what's eluded us for so long. Yet for all our ingenuity, dark matter might still slip through. Some theories suggest it's so weakly interacting that no detector we build, no matter how sensitive, could ever spot it. Others argue we're simply asking the wrong questions. Could dark matter be an illusion, a sign that gravity works differently on cosmic scales? Modified gravity theories like MAND haven't been ruled out entirely, though they struggle to explain phenomena like the bullet cluster. Or perhaps dark matter isn't one thing but many, a mix of particles, black holes, and other oddities defying a single explanation. What's fascinating is how much we've learned even in the absence of answers. Dark matter's stubborn invisibility has forced us to rethink the universe's architecture. We now know it's the scaffolding for galaxies, the unseen hand shaping cosmic history. And every dead end in the lab teaches us where not to look, narrowing the possibilities. The real twist, even if we never directly detect dark matter, its influence is undeniable. Like wind shaping dunes without being seen, dark matter's gravitational pull is etched into the cosmos. Future astronomers might not find it so much as accept its role in the grand equation, much like we did with black holes long before imaging one. So, will we solve dark matter? Maybe not in the way we expect. Science rarely unfolds like a textbook. It's messy, unpredictable, but every mystery solved spawns new questions. Whether dark matter's nature is revealed in our lifetime or remains a riddle for future generations, the pursuit itself reshapes our understanding of reality. After all, it's not just about the destination, it's about how the journey expands the universe of our imagination. And who knows, the next great discovery might come from a detector buried deep underground, a telescope orbiting 1 million miles from Earth, or an idea so radical it rewrites the rules. Until then, the hunt continues, one hypothesis, one experiment, one cosmic clue at a time. So stay curious. The universe's greatest secrets are still out there waiting. Now, let's shine a light on a tantalizing clue in the dark matter hunt. An anomaly so puzzling it sparked debates for over a decade. The Fermi Gamma Ray mystery might just hold the key to unraveling dark matter's secrets, or it could be the universe playing another one of its cosmic tricks. At the heart of this enigma is NAS, a Fermi Gamma Ray Space Telescope, specifically its Large Area Telescope, or LAT, which has been scanning the skies since 2008. What it's found in the heart of our galaxy has scientists both excited and cautious. An unexpected excess of gamma rays, the universe's highest energy light, concentrated near the Milky Way's core. Here's why that matters. Some theories suggest dark matter particles, when they collide, could annihilate each other and produce gamma rays. In other words, this glow could be the smoke from dark matter's invisible fire. But the plot thickens. Among this gamma ray haze, researchers spotted something even stranger. A faint but persistent signal at a very specific energy, around 130 gigaelectronvolts. This so-called line signal is controversial because it doesn't neatly match known astrophysical sources like pulsars or cosmic rays. Instead, it aligns eerily well with predictions for certain dark matter particles like WIMP annihilating into pure energy. Imagine it as a fingerprint unique enough to hint at dark matter's identity. Yet, as with all great mysteries, skepticism is healthy. Alternative explanations abound. Could the signal be from undiscovered pulsars, super-dense stellar corpses spinning in the galactic center, or perhaps systematic errors in the data? The debate rages on, with some studies claiming the signal is real and others attributing it to background noise. Even Fermi's own team has cautioned that the evidence isn't conclusive. What makes this mystery so compelling is its potential to bridge theory and observation. If the gamma-ray excess is from dark matter, it would not only confirm the particle's existence but also reveal its mass and how it interacts. That's like finding a Rosetta Stone for the invisible universe. But until we rule out every other possibility, the Fermi signal remains a tantalizing, maybe a cosmic whisper we're still learning to decipher. So where do we go from here? Future telescopes like the proposed AMIGO or upgraded gamma-ray detectors could provide sharper data. Meanwhile, theorists are refining models to predict what other smoking gun signals dark matter might leave. One thing's certain, the Fermi mystery reminds us that sometimes the universe hides its biggest secrets in the faintest glimmers of light. And whether this clue pans out or not, it's driving science forward, one gamma ray at a time. Next up, another piece of the puzzle: actions. The dark matter candidate so elusive it's been called a ghost particle. But that's a story for another segment. Now, let's turn our attention to a ghostly contender in the dark matter hunt: actions. These hypothetical particles, so ethereal they could pass through entire planets without a trace, might just hold the answer to one of cosmology's biggest riddles. While WIMP have dominated the dark matter conversation for decades, actions are quietly emerging as a compelling alternative, thanks to ingenious experiments designed to catch these cosmic phantoms in action. The story of actions begins not with dark matter, but with a puzzle in quantum physics. In the 1970s, scientists noticed something odd: the strong nuclear force, which holds atomic nuclei together, mysteriously respects a symmetry called charge parity, or CP, to an almost perfect degree. This shouldn't be the case according to theory, and so physicists proposed a new particle to explain it: the action. What's remarkable is that this same particle, devised to solve a quantum conundrum, also fits the bill for dark matter. Actions would be incredibly light, up to 1 billion times lighter than electrons, and interact so weakly with ordinary matter that they'd be nearly invisible. Yet, if they exist in vast numbers across the cosmos, their combined gravity could account for the missing mass we observe. So how do you detect something so elusive? Enter ADMX, the Action Dark Matter Experiment, a marvel of ingenuity housed at the University of Washington. ADMX operates on a brilliant principle. If actions are floating through space, they might occasionally convert into photons, particles of light, when exposed to a strong magnetic field. The experiment uses a supercooled cavity chilled to near absolute zero, bathed in a powerful magnetic field. If actions pass through, they could produce faint microwave photons, which ADMX ultra-sensitive detectors are designed to pick up. It's like turning the entire detector into a cosmic radio tuned to the faintest possible station, the whisper of actions. But ADMX isn't alone in this hunt. Across the globe, experiments like KOLTASK in South Korea are pushing the boundaries even further. Koltask employs a similar approach but with enhanced sensitivity, using multiple cavities and advanced quantum amplifiers to sift through the noise of the universe for that telltale action signal. Meanwhile, initiatives like MadMax in Europe are exploring higher frequency actions, broadening the search beyond ADMC's range. Together, these projects form a global net, casting wider and finer meshes to catch what might be the universe's most evasive particle. The stakes couldn't be higher. If actions are out there, they'd not only solve the dark matter mystery but also reveal profound new physics. Unlike WIMP, actions wouldn't require extensions to the standard model of particle physics. They'd fit neatly into existing theory, elegantly tying up multiple loose ends. Plus, their discovery would open a window into the early universe, as actions are thought to have formed in the chaotic aftermath of the Big Bang, freezing into place as the cosmos cooled. Yet, challenges remain. Action detectors must contend with a universe full of background noise, cosmic rays, thermal vibrations, even human-made radio signals. Separating a genuine action signal from this cacophony is like listening for a single note in a symphony. That's why researchers are constantly refining their methods, developing quantum sensors and AI-driven data analysis to tease out the faintest hints. What makes this search so thrilling is its blend of patience and creativity. Every null result, every time an experiment fails to detect actions, tightens the constraints on where they might be hiding, guiding theorists toward new ideas. And if one day a detector like ADMC's or Koltask catches that elusive signal, it could rewrite our understanding of the universe's hidden architecture. Until then, the hunt for actions remains a testament to human curiosity, a quest to find the invisible threads woven into the fabric of reality itself. Speaking of cosmic threads, our next mystery takes us even deeper into the dark matter tapestry, where filaments of unseen matter stretch across the cosmos, shaping everything we see. But that's a story for another moment. Now, let's shift our gaze toward the cutting edge of cosmic observation, where the James Webb Space Telescope peers into the depths of the universe, hunting for shadows and whispers of dark matter's influence. This revolutionary instrument isn't just rewriting the story of the cosmos. It's poised to uncover clues about dark matter's role in shaping the earliest structures of existence. One of the most tantalizing prospects is the hunt for dark stars. These aren't stars as we know them, no blazing nuclear fusion at their cores. Instead, dark stars would be colossal, faint giants powered by the annihilation of dark matter particles. Imagine a behemoth hundreds of times the mass of our Sun, glowing dimly as dark matter collisions provide its energy. Theoretical models suggest such objects could have formed in the infant universe where dark matter was densely packed. If they exist, their faint infrared glow might still linger in the distant cosmos, visible only to an eye as sensitive as Webb's. The telescope's unmatched infrared capabilities make it the perfect tool for this search. Unlike Hubble, which sees primarily in visible and ultraviolet light, Webb's instruments are tuned to detect the heat signatures of ancient objects whose light has been stretched into the infrared by the expansion of the universe. If dark stars are out there, their telltale emissions could be hiding in Webb's deep field images, strange, extended objects with unusual spectra that don't match any known type of star or galaxy. Researchers are already scouring early Webb data for anomalies that might fit the bill, like oddly smooth or puffy structures where dark matter's fingerprints could be etched. But dark stars aren't the only quarry. Webb is also revealing how dark matter sculpted the first galaxies. Simulations suggest that dark matter's gravitational pull acted as a cosmic scaffold, guiding ordinary matter into the filaments and clumps that birthed galaxies. Webb's observations of ultra-distant galaxies, some dating back to within a few 100 million years of the Big Bang, show surprising patterns. Many are smaller, denser, or more misshapen than predicted, hinting that dark matter's distribution in the early universe wasn't as uniform as we thought. Some even appear to be rotating too fast for their visible mass, echoing the same dark matter mysteries we see in modern galaxies. Then there's the puzzle of galaxy formation itself. In a universe without dark matter, gravity alone would take far longer to pull gas and dust into galaxies. Yet Webb has spotted fully formed galaxies earlier than expected, suggesting dark matter's invisible hand accelerated their growth. Some theories even propose that dark matter's unique properties, like its inability to radiate heat, allowed it to collapse into dense halos faster than normal matter, creating gravitational wells where galaxies could rapidly assemble. Yet with every answer, Webb raises new questions. Why do some early galaxies lack the heavy elements we'd expect if dark matter guided their formation? Could dark matter interactions have suppressed star formation in certain regions, leaving behind failed galaxies? Webb's detailed spectra, which break starlight into chemical fingerprints, are helping scientists trace how dark matter influenced the cosmic recipe of elements. The telescope's role isn't just about spotting dark matter's effects, it's about testing alternatives too. For instance, if modified gravity theories like MUND were correct, early galaxies should look markedly different than they do in dark matter models. Webb's crisp images are putting these ideas to the test, measuring the shapes and motions of primordial galaxies with unprecedented precision. So far, the data leans toward dark matter's existence, but surprises could still lurk in the shadows. What makes Webb's mission so thrilling is its potential to connect dots across time. By studying the oldest galaxies alongside their modern descendants, we might finally see how dark matter's influence evolved, whether it clumped differently in the past or if its interactions with ordinary matter changed over billions of years. Each snapshot from Webb is like a frame in a cosmic time-lapse, revealing the invisible forces that shaped everything. As we await more revelations, one thing is clear: Webb isn't just a window into the past. It's a mirror reflecting dark matter's enduring enigma, showing us how much remains hidden in the void. And with every new observation, we edge closer to unraveling the universe's darkest secret. But our journey doesn't stop here. Next, we'll venture into a realm where galaxies seem to defy the laws of motion, a phenomenon so strange it could rewrite our understanding of dark matter's grip on the cosmos. Now, as we wrap up this cosmic journey through the invisible architecture of the universe, let's take a moment to reflect on the sheer scale of what we've uncovered. These 25 mysteries of the dark matter Webb aren't just puzzling gaps in our knowledge, they're doorways to reimagining everything we thought we knew about reality. From the ghostly pull of missing mass in galaxy clusters to the mind-bending possibility of dark stars, each revelation peels back another layer of the cosmos' deepest secrets. Think about how far we've come. We started with Zwicky's missing mass problem nearly a century ago, and now we're debating whether dark matter could be a whisper from another dimension or a shadow of a parallel universe. We've seen how it bends light around galaxies like a cosmic prank, how it might have birthed the first stars without fire, and how its fingerprints appear in places we never expected, like the eerie stillness of cosmic voids or the frantic dance of galaxies fleeing the dark flow. Every discovery, from the controversial Dharma signals to the unexpected smoothness of Dragonfly 44, chips away at our assumptions, revealing a universe far stranger than we dreamed. And yet, for all we've learned, the greatest triumph might be realizing how much we don't know. The Hubble tension reminds us that even our best measurements of the universe's expansion don't agree. The satellite galaxy puzzle hints that our simulations of dark matter's behavior might be missing a crucial piece, and experiments hunting for particles like actions or WIMP keep coming up empty, leaving us to wonder, is dark matter hiding in plain sight, or are we searching for the wrong thing entirely? That's the thrill of science. It's not about neat answers, but better questions. Each mystery we've explored today isn't a dead end, it's a trailhead. The James Webb Telescope is already rewriting the story of dark matter's role in galaxy formation. Upcoming missions like Euclid and LISA will probe its influence with even sharper tools. And somewhere in a lab or observatory, a researcher might be staring at data that could crack this case wide open. So here's my question for you. Which of these 25 mysteries grabbed your imagination the most? Was it the enigma of dark photons, the quantum weirdness of actions, or the spine-tingling possibility that black holes might be dark matter? Drop your thoughts in the comments. I read every one. And if you're as hooked on cosmic mysteries as I am, don't forget to subscribe and hit that notification bell. The universe has plenty more secrets to share, and I'll be here to unpack them with you. Until next time, keep looking up, because the darkest corners of space might just hold the brightest revelation.